Okay, good morning. Actually, I recorded this on Sunday, so that's why I do not want to show you my face as I have not tidied myself up yet. So anyway, this will be the lesson on the remaining of worksheet 15.0, which is your sound worksheet. So please get ready. You should have a hard copy with you. So we will continue from page 3, and I believe that at this point of time you would have completed question 4 A and B. I think for A part 2 we have gone through quite extensively in class. So just remember when we are dealing with echo and we are using echo to determine a certain distance, just remember that for your echo it has actually traveled 2 times the distance. So if you are using 15 seconds, then you need to divide the distance determined by 2. And in another word, actually the sound wave actually take just 7.5 seconds to travel from the emitter to the seabed. So depending on whichever methods you want to use, whether you want to use 2D equals to speed times time, or you want to divide the time first and you just calculate directly, both methods are fine. And the second thing that I would like to recap is that for this case, I will give you a more detailed explanation to why you hear sound differently when you speak into a microphone and when you what you hear yourself, okay? But as of now, I would like you to just remember that the frequency of sound will essentially remain constant when it passes through different medium. So it is very similar to your water wave. Remember in the wave chapter, when you have water wave traveling between a shallow region and a deep region, actually the water wave would have different speed. And in the deeper end, actually it would have high speed, and in the shallow end, it would have low speed. So if you apply V equals to F lambda, the same thing happened for water wave, that the frequency is actually constant. So whether you have low speed or high speed, what changes accordingly is actually the wavelength. So similar to sound, when a sound travel between air and a denser medium, in this case water, the speed would actually decrease or increase depending on the medium, and the frequency would essentially stay constant. So what actually changes is actually the wavelength. So this question A1 is actually to show you that the frequency remain constant, whereas the speed and the wavelength would change according to the density of the medium. So that's what A1 and A2 is trying to show you. As for part B, this one involved a little bit more on mathematics. So what happened is that down here there's no echo, it's just from the source to the receiver. So what is the source? The source is actually the explosion of the ship, and the receiver is actually these people floating on the sea. So essentially the sound will travel in all direction. So when you first hear the sound, of course, the sound that you hear must be the sound wave that is traveling in the shortest distance. So what I mean is that when an explosion happens, the sound will actually occur in all direction. And the first sound you hear, of course, will be the sound that reaches you in the shortest distance. And in this case would be the straight line between the source and the receiver. So that's why we are analyzing these two paths, the yellow path, which is the shortest path. Okay, so what happened is that because sound actually reaches you through both in the air and in the sea. So obviously sea consists of water, and water is a denser medium compared to air. The sound traveling in water will reaches you first. So the first sound that you hear is actually the sound traveling in the sea, and it reaches the receiver. And then after that, after some time, you would also hear the second sound, which is actually the sound wave traveling in air. So what the question is saying is that the first sound and the second sound is actually having a delay of 1 second. So if you want to express this context in mathematics, so essentially what you are trying to say is that the time taken in air, which is the longer one, right? This will take a longer time, minus of the time taken in water, in this case this would reach you at a shorter time, would be equals to 1 second. So this is the mathematical expression of this green highlighted sentence. So in physics, we are basically using mathematics to describe our world, and we have in previous lesson established that actually speed is equals to distance over time. So now what happens is that in our principal expression here, we have the subject in terms of time. So in this case, we can actually rewrite our equation with time as the subject, and we will have the equation distance over speed, right? And we can actually substitute this expression into our principal expression here. So after we do that, we can actually rewrite our equation as this. So distance over speed in air minus distance over speed in water is equals to 1 second. So since the distance is the same, because we can treat it as the same down here, so we can give it algebra d. So we would have d minus d over speed in air is actually 340, and then of course speed in water is 14501. Right, so here in this equation we will have only one unknown, and we can actually solve this. So of course I will let you play with the mathematics, and you should be able to get to this answer. So you make d the subject basically. Okay, so that is what we have covered in the previous lesson. So here what we have is that similar to light and waves, we will have different representation of sound wave. So for example, in wave, we can represent wave in terms of graphs. We have two graphs, do you recall? Yeah, we have the displacement position graph, we have the displacement time graph, and we have wavefront. So in this case, I just would like to focus on wavefront and its application to sound. So in this case, what we are seeing here, if you read this chunk, you can pause the video and read it, okay? And then after that, you can unpause, okay? So after you have read it, you will actually realize that what this diagram is trying to show you is that this wavefront represent the air layer before the sound wave actually travels. So actually this is what we call the equilibrium position of the air layer. So the undisturbed position of the air layer. And what happened is that these dots are actually also air layer. It's just that to avoid confusion with so many lines, they represent the undisturbed position as a line and the disturbed position as a dot. So what happened is that this is like a photo taken. So what happened is that the time now is actually frozen at a certain instance, and in this photo what they discover is that, for example, line number 1, the air layer number 1 has now shifted to this position where the dot is, so we can call this 1 prime, and so on and so forth. You will see this air layer number 2 has shifted here, and then air layer number 3 has shifted here. So in this disturbed diagram, the dots, we can actually see down here, you can see actually a compression forming, and we say that here is actually what we call the center of compression. And you will notice something that is quite interesting, and that is actually down here, the original position, which is line number 1, 2, 3, 4, and the disturbed position 1, 2, 3, 4. Can you see that the disturbed position of this air layer and the undisturbed position of this air layer, which is the blue one, actually remains the same. So at the center of compression, the amplitude is actually 0 because there's no displacement between the blue line and this red dot, right? This disturbed position. Yeah, and we can observe that the next place whereby there is no displacement. Can you find the next position where there is no displacement between the disturbed versus the undisturbed? Meaning that I want the dot to be on the line. Can you find the next position whereby there is no displacement? And I think most of you would be able to find that position around this region. And in particular, you can see this part and this dot are actually in the same position, and you can see that on the left and the right side of this position B, that the particles or the air layers are actually being stretched apart. So this is where we say that this is actually the center of our rarefaction. Right, and interestingly, again, you can see that the amplitude at the center of rarefaction is actually 0. So just from this diagram, what can you tell? What kind of information can you extract from this diagram? Well, number one is that we learn that our wavelength is actually from center of compression to the other center of compression, right? So what it means is that half a wavelength is actually from the compression to the rarefaction. Because in order to go from compression to compression, actually in detail is compression, rarefaction, compression, right? So actually we can actually find out, since this diagram is drawn to scale, we can actually find out that we can measure this, and this actually gives us half the wavelength. We can find this as well. And we can also find the amplitude of the wave. Now, if you look at a typical wave, right, where does the amplitude, this amplitude, where does the amplitude usually come out? It's actually from zero displacement, right? Here is zero displacement. So this is compression, rarefaction, compression. Am I right? Because this position, if you look at here, the yellow part, the green part that I've highlighted, you can see that the disturbed position is at the undisturbed position, meaning that there's zero displacement. That's why I draw the first dot over here. This one, the one that I highlighted in pink now. So this is the compression position, followed by the rarefaction position where displacement is 0, and then I would expect the compression to appear, the next compression to appear there. And you can see that between C and R, that is where the amplitude will actually form. So from here, I can count 1 dot, 1 dot, 2 dot, 2 dot. So it means that this must be my amplitude. So what is the definition of amplitude? Definition of amplitude is the maximum displacement between the disturbed and the undisturbed position. So now I have found the disturbed position. Where is the undisturbed position? Can you find it? So the undisturbed position must be here, 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 here. This is the center, right? So actually this disturbed position is coming from this red line, the undisturbed here. So where is the amplitude? The amplitude must then be given by this distance, right? This one here. Yeah, so actually from this simple diagram, we can extract wavelength because we can just measure this, multiply by 2. We can find the wavelength. We can also find the amplitude, right? Can we find frequency? Actually, we don't have any information about time or number of waves generated, so we can't find frequency. Can we find speed? Not really, right? Because V equals to F lambda. I can find the lambda, but I don't have information on F. So you need to know from what representation, what information you can extract. So down here, what we have is that now that we have dissected this picture, we can now answer A, B, and C. So let me erase all this thing so that it doesn't distract us. And then we look at part A. So part A, we are to actually mark the position C and the position R for compression and rarefaction. So now we know that this is the center of compression and this is the center of rarefaction. So we have analyzed that. Then we have to determine displacement of the particle from its undisturbed position as C and D. And we have already said this is the undisturbed position, this is the disturbed position. They are at the same place, so displacement will be 0. And in our case, remember, we are using a ruler, so precision is 1 dp, right? Okay, now I have to measure the wavelength, and we have done that, right? We already know that from here to here is half a wavelength, so use your ruler, it's drawn to scale, measure it, and then multiply by 2. Remember, you are using a ruler, so the precision is up to 1 dp. Okay, for your part D, we have to measure the amplitude, and we have already done that. We know that the amplitude will appear between C and R. So let's write this down as notes, so you would remember. So now we know that your amplitude, which is actually your max displacement, it will appear between your C and your R. So we know that that would be this place. This is the undisturbed and this is the disturbed. So use your ruler, measure this green color part. Remember you're using a ruler, so 1dp. Yeah, so don't worry, this thing I have done it with you, and you are supposed to refer to this question 5 when you are doing, let me see, later on. I think the next lesson I will give you 1 period to actually finish your worksheet 15.1. I hope I have uploaded it. Yep. So you can look at 15.1 and you can see that one of the question, this question 4, actually is very similar to your question 5, and you can actually practice and see if you really understand and internalize the knowledge that I just shared with you. So question 5 is a direct reference to question 4, and I try to make things easier for you by labeling 1 2 3 4 the air layer. So instead of the dots, I bring down the diagram and give you the disturbed position in figure B in terms of lines. Okay, so that is that. So let's continue with 15.0. So now that we know of this line and dot representation, then of course we have graphs, which is very similar to your waves. So down here, EFG is actually a continuation of question 5. So let's continue. So now I am being asked to complete a displacement position graph, and I have to share as much data as possible in my axis. So down here, let's say because I couldn't measure it from my iPad. So let's call this C and let's call this D. Okay, so I need to represent this data C and D in my new graph, and you notice that I purposely shifted the graph up so that the equilibrium position is no longer at 0. So now I know that the amplitude is D, right? This D. Yeah. So how do I represent that? If my amplitude is D, that means from this point to this point, it will have the length D. So meaning that down here, if I shift it up, then I would say that from here to here is also the amplitude. So therefore, this must be my D, and this will be 2D. Okay, so that's how I get the answer. Now, how about here? I already know my wavelength, right? So I know my wavelength, this is my wavelength, which I have measured, recorded in C. So now this one is how many wavelength? So let's take a pause for you to think. So this is 1 wave, right? This is 2 wave, and this is 3 wave, right? So this is 2 wave, 1 wave. So let's divide this wave into half. This is half, and from this half we can divide it into another half. So how many waves? I hope by now you will be able to figure out. This is 2.25 wave, or if you want, it is 2 1/4 wave. So you can get this here. Yep. And then after that, I have to label C, center of compression, and center of refraction in my sketch E. So we have already figured it out, right? So just now I was saying that down here there's no displacement, and R I also have 0 displacement. So meaning that it must be here. This could be my C, and if this is my C, then this, maybe I use black, this is my C, then this must be my R, and then this must be my C, so on and so forth. Of course, you can start off by saying that the first dot is R, then this one will be C. So it has to alternate, okay? It depends on what you want. And finally in G, now I have to sketch on the same graph. So since I'm sketching on the same graph, let me erase all these things so that you can see clearly how the sketch is done. Okay, the same sound, but now it is half a period has passed. So let's imagine that I took this picture at time equals to 0. And remember the gadget that I bring to class, the one that I turn it. I say that the wave like that, right? Let's say the wave is being generated like that. So after one period, what happened is that this wave would be pushed to this new position. Why? Because after some time, after one period, I would have generated a new wave, right? This red one is the new wave, and the green wave would have been pushed to here, right? And if I wait until the time t equals to 2 times of the period, then the red wave would have appeared here, the green wave would have been pushed down even further, and that is because by the second period I would have generated a new wave, the blue one. So as times go on, I'm going to push the wave front, the compression or the crest down the line, right, down towards the direction of wave travel. So this red wave is being pushed to here because one full period has passed. What if I only let half a period pass? So let's restart our deduction. So at the beginning, let's say I have one full wave and I'm generating the wave to push to the right. If I waited one complete period, my source would have generated a new wave, thereby pushing the old wave, the green wave, to the next position. This is when I let time equals to one full period. I would have pushed it by this and this much. So what if I let it generate for half a period? Well, in that case, then let me have some reference, right? So like that, right? Yeah. If I let it run for a full period, my green wave would be pushed here. So if I didn't let it run for a full period, I let it run for half a period, that means my green wave would have been pushed to just here. Agree? That means my green wave would appear here, and if I only waited half a period, it means that I only give half the time for the source to generate half a wave. So half a wave generated will be like this, correct? So I only push it like that, and you can see that by this logic, what we can do is that we can reverse engineer. Can you see that my crest has just moved to where the throat is, right? Can see? Now, be mindful, is this dot being carried to here? The answer is no. This dot is vibrating up and down. So this dot, when half a period went by, it will appear here. Okay, this dot does not get carried to the left or the right. It is vibrating up and down. Okay, and of course, since it's longitudinal wave, in actual fact it is vibrating left and right. Okay, it's just that this representation, we are looking at it, we are representing it differently. Okay, so just be careful, the particle of the medium does not get carried. It's the crest that is moving or the compression that is moving. So in this case, after half a period, where will this crest go to? It will appear somewhere here. So if I were to draw this waveform after half a period, then I know that the crest would appear here. This means that this thing is here, and then I can draw here, then here, then here, then here. So this red wave represents the displacement position graph after time equals to half a period. Got it? Yeah, and you get to practice that in your homework, I think. So here you can see that you need to sketch again a displacement position graph, and I would expect you to label the y and the x-axis similar to this. Okay, can? So that is that. Okay, now that representation is over, you also would need to, that is the last part of your sound, and that is how to describe sound. So at the very beginning, I told you sound can be described by two things, the pitch and the loudness. So pitch is like high pitch, low pitch. Loudness, of course, you know, if I shout at you, it's very loud, or it's like whisper, then it's low. So if I do that in a mic and I transfer it in, and I translate that into a signal, how would the sound signal look like? Okay, so pitch, if you look at the waveform, is that it is being controlled by your frequency. So if I look at this waveform, waveform A and waveform B, which one has a higher pitch or a higher frequency? So how do you compare? Let's say you just take this time. So let's say I take this as a 10 second. So within 10 seconds, you can see that waveform A have only one wave. But waveform B has already like 1, 2, 2.5, that kind of wave. So which one has a higher frequency? Obviously, wave B. So we say that wave B has a higher pitch because it has a higher frequency. And how about loudness? Loudness comes from the amplitude. That means from here to here. So you can see that the amplitude here is 0.1 and the amplitude here is 0.12. So which one has a louder volume or a higher loudness? Of course, waveform B. So what are the questions is like? The question is like, if you are asked to describe the sound wave, so how to describe the sound wave? Well, you can describe it in terms of pitch and loudness. So here you will say that your wave B is louder and has a higher pitch. Now don't stop here because you are going to send your answer to Cambridge. So louder than what? Then please complete your sentence. Then wave A. Okay, explanation, well, it is very easy because your wave B has a higher, so loudness, right? Loudness corresponds to higher amplitude and pitch corresponds to the frequency, then that of wave A. Okay, so I think this is the last part. Yep, this is the last part of your sound chapter. You need to know that sound, what we hear as high pitch is actually high frequency sound wave, and if we hear a loud sound, it's actually high amplitude sound wave. So if I ask you a question, why is it that echo usually comes back softer? Well, that is because why? When the sound reaches the hard surface and get reflected, part of the energy is being absorbed by the reflecting surface, and we say that the energy carried by the wave is given by its amplitude. And since for sound, amplitude is related to loudness, after the reflection, less energy is carried by the echo sound wave, and so echo sound wave will definitely have a smaller amplitude, and a smaller amplitude means that it has a softer sound. Yeah, so you need to learn how to use this parameter to explain phenomenons. So nowadays in O level, they always give contextual question that asks you to explain phenomenon, and your job is to actually relate this phenomenon and then break it down into parameters, and then use the logics or the laws that you learn in lesson and to relate them. Why is it that this phenomenon is like that? Why is it echo is softer? Well, because softer means, or you can reverse engineer, softer means it has lower amplitude. Amplitude means amount of energy carried by the wave. So where does the energy goes? Oh, it must be lost during the reflection. Well, you can explain that way as well. Yeah, from end to front or front to end, up to you. Okay, so I will stop here, and in the next home-based learning lesson, please use that period to actually finish your 15.1 and then hand it up on Monday when we meet again in the school week. Okay, ciao, bye bye.